As we have seen, effective use of S-auto is not fully automatic. One needs to provide appropriate options and explicitly list all necessary lemmas and all constants that need unfolding. Finding the right lemmas in a large library is tedious and time-consuming. The hammer tactic attempts to automate this. The hammer tactic works in 3 phases: machine learning premise selection, translation to external ATP systems, and proof reconstruction. In the premise selection phase, the hammer tool selects up to a few hundred lemmas likely useful for proving the goal. I'll be talking about lemmas, but actually any accessible definition can be selected regardless of whether it is intended to represent a theorem or not. In the premise selection phase, simple but fast machine learning techniques are used: naive Bayes and k-nearest neighbors. It is crucial here that learning is fast, because it is repeated every time the tactic is invoked in order to include all accessible lemmas for premise selection, also those proven earlier by the user. Premise selection is just a crude pre-filtering step. The second phase is the translation to external ATP systems. ATP is an abbreviation for Automated Theorem Prover. The goal and the lemmas pre-selected in the first phase are translated to the logic of the ATPs. The goal as the conjecture, the lemmas as axioms. The ATPs are then run on the translation. When they succeed, they return the names of the lemmas they actually needed. The third proof reconstruction phase uses S-auto or other tactics to finally prove the goal in the logic of Coq, using the lemmas returned by the ATPs. So CoqHammer uses the ATPs only as precise filters to select the lemmas needed to prove the goal. Beyond the information about the dependencies, CoqHammer doesn't look at the ATP proofs at all. It reproves the goal from scratch. CoqHammer uses classical first-order ATPs, but it then tries to reprove the goal in the intuitionistic logic of Coq with no additional axioms. So there is a mismatch of the logics, and sometimes it might be impossible at all to reprove the goal using the returned ATP dependencies. Also, the S-auto proof search procedure is weaker than state-of-the-art first-order ATPs. So it sometimes fails when an intuitionistic proof is possible, but too difficult. An important thing to note is that the target external tools of CoqHammer are general first-order ATPs, not SMT solvers. CoqHammer can use some SMT solvers because in practice, they may often be used in the same way as general ATPs. But CoqHammer will never use any of the modulo theory features of SMT solvers. Natural numbers, lists, and so on are not translated in any special way, and the SMT solvers will see them as uninterpreted data types. SMT Coq is a project which aims to connect SMT solvers to Coq. The aim of the hammer tactic, in contrast, is to automatically find lemmas necessary to prove the goal from a large collection of all accessible lemmas. Okay, that's enough of a general introduction. Let's see how to use the hammer tactic in practice. To use the hammer module, which contains the hammer tactic, you first need to install the full hammer system. Once you load the hammer module, the following 2 commands are available. The hammer version command displays the version of the CoqHammer system you're using. I'm using here a development version for Coq 8.11. Hammer objects tells us how many objects are available for premise selection. Okay, the hammer tactic is supposed to be fully automated. So usually all you need to do is just type hammer and see what happens. Here we use hammer to prove that any natural number either is odd or its successor is odd. First, the Hammer tool is extracting features for machine learning premise selection. To do this, it needs to look at the proofs of all accessible lemmas, including opaque proofs. The features are cached, so this will be faster the second time we run the tactic. Once it has extracted the features, it runs the provers, the external automated provers, in various configurations. Once a prover succeeds, the returned dependencies are displayed. Here, the CVC4 prover succeeded. It used 64 premises pre-selected with the k-nearest neighbors algorithm. Once a prover succeeds, Hammer tries to reconstruct the proof using variants of S-auto and 3 standard Coq tactics, E-auto, first order congruence. Here, the standard Coq tactics didn't succeed. So Hammer tried the first batch of S-auto variants. The H-auto LQ-on tactic worked. The idea is that you then replace, upon success, that you replace the Hammer tactic with the tactic shown in the response window. For illustrative purposes, I only outcomment the Hammer tactic. Here is the tactic copied from the response window. The success of Hammer is not guaranteed to be reproducible. In fact, it's often not, sometimes even not on the same machine. The Hammer tactic depends on external ATPs, which are run with a time limit. The final S-auto-based reconstruction tactic, here, searches for a proof in the logic of Coq with no time limits and no dependence on external tools. Its success is always reproducible. Here is a similar lemma about evenness. The predict tactic runs only the first premise selection phase of Hammer. Predict n pre-selects n dependencies likely useful for the current goal. By itself, this machine learning pre-selection is too crude to be very useful. One often needs to ask for a few hundred dependencies to have all the necessary ones among them. Here, the predict tactic displayed 16 dependencies selected by machine learning for the current goal. We run the Hammer tactic again. The lemma is analogous to the previous one, so Hammer can prove it. Since the features have been cached by the last invocation of Hammer, we see that premise selection is now much faster. Here is a more interesting lemma taken from one of my formalizations. This lemma cannot be proven by S-auto alone or by Lia because of exponentiation. Lia can't handle it. We see S-auto fails. Hammer can prove this lemma because it can select helper lemmas from the standard library. It did succeed here. Now a lemma about lists, which essentially combines 3 lemmas from the standard library. It is a bit artificial, just designed to show that Hammer can find these 3 lemmas. Now a less artificial lemma about lists, which one could easily need in a formalization. Like S-auto, Hammer is not designed to do proofs by induction. If induction is needed, the induction tactic must be written first by the user. Then one can try Hammer for the generated subcalls. Here, Hammer can solve both subgoals using variants of standard Coq tactics, congruence and E-auto. Now, some lemmas about permutations of lists. Let's try to prove this lemma with Hammer. We are waiting. Unfortunately, the ATPs didn't manage to find a proof. One can try increasing the ATP time limit as suggested in the response message, but if the lemma is too difficult, increasing the time limit doesn't help. One common technique is to formulate an easier lemma from which your desired lemma follows, and then prove both lemmas with hammer. We will try to do this here. Here we have the same lemma, but without x and y swapped. It should be a bit easier to prove. Indeed, hammer manages to find the right dependencies here. Yes, it did find them. And now it's trying to reconstruct the proof. The first reconstruction batch failed. It tried the tactics from the second batch, and one of them worked. I have copied the reconstruction tactic here. Now our desired lemma can be proven with hammer, because hammer can use this previous helper lemma we've just proven as one of the dependencies. So we run in hammer, and it did find a proof. Occasionally, some of the returned dependencies are not necessary. One can then try to minimize the dependencies manually by trying to delete some and see if everything still works. That's what I've done here. And it turns out that only those 3 dependencies are necessary. If the ATPs return at least 8 dependencies, then hammer tries to perform this kind of dependency minimization automatically. This can be controlled with the set hammer minimization threshold option. A general advice is to use hammer to prove entire lemmas which are stated separately. Using hammer to prove subgoals in a larger proof is often less effective. One reason is that the machine learning premise selection can get confused by the presence of unnecessary hypotheses in the context. So it's best to think about the property you need, abstract it into a separate lemma, and then try to prove this separate lemma with hammer. If this lemma turns out to be too difficult for hammer to prove, then you may try breaking up this lemma into a few more lemmas. Here we have another lemma about permutations. The vampire prover with 64 dependencies preselected with naive bias succeeded. But it returned at least 8 dependencies, so automatic dependency minimization kicked in. It takes a while. Dependency minimization succeeded. We are left with 4 dependencies. Another lemma about permutations. This one is easily shown using the lem_perm1 lemma, which hammer can find. It can use any of the lemmas that are accessible at a given point in a formalization, not only lemmas from predefined libraries. It succeeded using lem_perm1 and permutation sim. Here is the reconstruction tactic. Here is an example of a lemma on which the ATPs succeed, but proof reconstruction fails. Let's look at it. Now, the hammer tactic is trying consecutive batches of reconstruction tactics. This finally failed. And it displays some suggestions about what can be done here. Let's try to create the proof manually using the returned dependencies. It's a bit annoying that in proof general, you can't really see those dependencies anymore once the tactic has failed. You need to then change to the Coq buffer to see the entire output of Coq, which includes what was written before. So here we have just 2 dependencies. Minimization succeeded, but the proof could not be reconstructed by S-auto-based reconstruction tactics. So let's try to write it manually using these two dependencies. So we do the intros, and we rewrite with list appcom cons. And we see here why the reconstruction tactics failed. As mentioned in a previous video, currently one of the limitations of S-auto is that it's not very good at rewriting. It will just blindly try to use the rewrite tactic without controlling which subterm exactly is being rewritten. And here we need to rewrite with the appcom cons lemma again, and the subterm we need to rewrite is not the one which would be rewritten by default. So we need to use the pattern tactic phase first. S-auto won't do that by itself. An important thing to keep in mind is that the external ATPs used by the hammer tactic are classical, but proof reconstruction with S-auto is intuitionistic. It may happen that the ATPs find a classical proof, but it is not possible to intuitionistically prove the goal with the returned dependencies, or it's very hard to do so and proof reconstruction fails. This actually happens relatively rarely. In practice, the dependencies returned by classical ATPs usually suffice for an intuitionistic proof, but sometimes they don't. An obvious example is the excluded middle axiom here. Of course, excluded middle can be proven classically without any dependencies at all, but is obviously not provable intuitionistically. We see an ATP succeeds immediately, but the proof cannot be reconstructed. Another important point is that because of its reliance on external first-order ATPs, Hammer will fail on most goals which require some non-first-order reasoning. In particular, Hammer's effectiveness is very poor on goals making essential use of Boolean reflection, sophisticated dependent types, or even higher order functions or predicates. Such goals can often be solved by S-auto with manually selected dependencies, but the hammer tactic will fail. This first order limitation is not as fundamental as it might seem. The success rate for non-first order problems could be improved with a more sophisticated translation, but this remains future work.